welcome to this afternoon session. I'm now going to present some of the tools that we have been using in all the previous presentations that you have seen from our group. So I mainly present PAIOS hardware and a bit of the software and the fitting. So to start, let's first consider how classical research is often done in a very simplified graph. So I see classical research as this. So you fabricate your device, then you do some characterization, try to understand your device. Mostly, why is my device not working? Then you go to a next experiment, try to understand it. You go to the third experiment, the second experiment, third experiment, and you try to understand. And once you have understood what's wrong with your device or what you can make better, you create a new concept and you start all over again. The problem with this, when we're working with perovskite or organics, is very clear, because maybe the third experiment you've performed on your device was 2 weeks later, and your device has already been degraded in the meantime, so it's not the same device anymore. And the second reason is clear. You need many different measurement tools. So as what you see here, like impedance analyzers and oscilloscope and lots of different equipments, it's time-consuming and it's difficult to compare. So that's what brought us to the idea to create PAIOS, because in PAIOS the concept is that we have all the characterization in one tool. So this simplified scheme looks much simpler because we create still the device, we put it connected to PAIOS, and then we run a full routine that characterizes all the relevant characterization techniques. So for example, here it measures IV curve and CELIV and impedance, capacitance-voltage and transient photocurrent, for example. So it measures everything automated after each other, and then you can go later and look at the data, try to understand your data and go up. So our goal is to provide like a tool that helps you to fasten your research. So to kind of accelerate this circle of understanding the physics of a device and creating a new device. And that's why we have developed PAIOS. PAIOS has currently a bunch of available techniques that one can use. Quickly go through one of the techniques I've also shown in the presentation this afternoon before. So you can measure impedance spectroscopy with offset light and offset voltage. It can measure Photo-CELIV and dark CELIV. So this is a technique used to extract charge carrier mobility. It can measure capacitance-voltage. It can measure dark injection transients. This is a technique that is often used to measure the mobility of monopolar devices. It can measure transient photovoltage. This, like this here, TPV. This is a very famous famous technique to measure charge carrier lifetimes. It can measure charge extraction here. So with this, you can measure the charge carrier density at open circuit voltage. It can do, of course, just regular IV curve, as every system can, with different light intensities, for example, or here as an IV curve in the dark of an OLED. It can do transient electroluminescence. So you measure how the luminescence of an OLED, like kind of the turn-on behavior of an OLED. It can measure transient photocurrent in case of a solar cell. It can measure IMPS and IMVS. These are two techniques that have been used a lot in the dye-sensitized community, but they're also interesting to study perovskite solar cells and organic solar cells. So what you do here, it's like impedance spectroscopy, but you do it with light instead of with voltage. So you have a light intensity, a certain offset, and then you modulate your light intensity. So you modulate it with a certain frequency, and then you measure the current, and you make a ratio between the current and the light intensity, and you plot this over different frequencies. This is then IMPS, so intensity modulated photocurrent spectroscopy. It can also be done at VOC, and then you keep the current constant, so keep the current at 0, and then you measure the voltage instead of the current, and then it's called intensity modulated photovoltage spectroscopy. This is then very much related with transient photocurrents, the result. And last but not least, a technique that we have invented, it's called MELS. It's like impedance spectroscopy, but you look at the electroluminescence signal. and that comes out from an OLED, and then you calculate again this quantity. From that, you can also learn some stuff about charge carrier mobility, for example. So we have the PAIOS can be used for OLEDs and for solar cells. So there's two versions. In one case, you just use an LED to illuminate the solar cell, and in the OLED case, it's vice versa. We use the OLED to create the light, and we measure it with a photodetector. So there's this measurement table that comes with it. I'll show it a bit later during the demo. So that makes the contacting very flexible. So you can use any substrate, and you can contact it with these flexible probes here. Okay, so let's guide you through some of the features I will show later in the demo. What we very often do is so-called sweeping. We not only perform one experiment, we perform several and vary one experimental parameter. So for example here, this is a Photo-CELIV, and what was varied is the light intensity. You see it here. So PAIOS performs the same experiment several times after each other, varying the light intensity. So for example here you see that the more light you have, the more charge is extracted. So you can see how systematic your device behaves. Then it's not only a measuring tool, it's also a database. It means you can measure several devices and then compare them directly in the software without tedious export to MATLAB and then comparing the stuff there. You can just multi-select and directly compare what you see here, for example, where 4 different cells are compared. Then we have some extra tools that help you analyzing the measurement results. For example, you can show RC effects. So you extract the R, so the series resistance, and the C, the capacitance. And then you can, for example, here in a CELIV curve, you can show the displacement current. So here, the red curve here, this is the measurement, and the black curve, this is the displacement current. So you can easily analyze what is displacement current. You can also subtract the current from the displacement current from the current, so it helps you to analyze. And then we have developed a bunch of simple techniques where you can extract simple parameters. So for example, so this is what we call basic post-processing, because the more advanced post-processing, this will be when we then use the ZFOS simulation tool and do numerical fitting and so on. That's why this is the basic post-processing. And you see here it starts with equivalent circuit fitting. So this is a tool, an analysis method that many people use to analyze impedance spectroscopy data. But for example, we can also determine the luminescence lifetime from a TL decay, or we can do a Schottky analysis, or we can extract the mobility from Transient Electroluminescence. So there's lots of different tools that help you easily, quickly analyze some measurements. One example I show a bit more in detail here. This is Photo-CELIV. I've shown you in my previous talk that there is a simple formula that you can use to analyze. You put in this peak time, so the time where the current reaches its maximum. You put in the ramp rate, and from that you calculate the charge carrier mobility. And this is automatically done here, what you see, so that the peak is marked in red with this tool, and it exports you here the mobility, for example, dependent on the light intensity and so on. This is equivalent circuit fitting, what I showed before. So we have just some easy circuits you can choose, but you can also put in some own formulas and then use our fitting algorithm to just fit these equivalent circuits to your measurement. Once you have extracted different parameters, for example, you have studied different materials and you have extracted the charge carrier mobility, you can then just easily create such bar plots or just some plots to compare your result. For perovskite solar cells, it's very tricky to measure them because they have different effects on different time scales. So you have effects that you already start seeing in the microsecond regime, but there's also effects that last over seconds. And this makes it a bit difficult to analyze. So what we did is we tried to make the dynamic range of the system as broad as possible. And we call this feature so-called FlexRes. So flexible time resolution. And it works like this. So let's imagine you use a classical oscilloscope and you can maybe measure 10,000 points. What you see here is then when you just plot it linearly, you see there's not real difference. So you see just the black curve here. When you plot it in log, you see, of course, because of the linear time sampling, you miss all the interesting features that are faster than your time step. So what we do is we measure internally with up to 30 million time steps, and we then convert this to a logarithmic time grid, some time spacing. That's why you see the red curve is measured by PAIOS, and you see there's a lot of dynamics here, but you still get the slow dynamics too. So you get here up to 7 orders of magnitude in time with one-shot measurement. Because in perovskite, you may think you could also measure it several times and then stick it together, but the experience is that the perovskite solar cells don't like that very much because they change a bit in the meantime, and then it doesn't match. So like this is especially for perovskite solar cells or for other devices with broad dynamic ranges. This is very, very interesting. What we can also do is pulsed IV curves, and before we have seen the talk about this self-heating. So self-heating is a problem that you warm up your device during measurement, and if you want to avoid this, you can just measure an IV curve with short pulses, and this is what you can do here, and you get also a nice dynamic range in current and a nice resolution, and you avoid heating. For perovskite solar cells, what you often see in publication, especially in the ones from Brian O'Regan and Philip Collado, what they often do is they name it tabbing. We call it preconditioning. It means we first apply a certain voltage to a perovskite cell for, let's say, a minute or a light intensity, whatever, for a certain time to precondition the ions, and then quickly after we do an experiment. And this looks like this. So, for example, this is the transient photocurrent onset of a perovskite solar cell, where you see without preconditioning, it looks like the red curve here, and the longer you precondition, the faster the current rise is. So this is very interesting when you do characterization of perovskite solar cells, because when you start your characterization, you want to have the cell in a somehow defined state. And with perovskite, when you just start measuring and you've done some other measurements before, you don't really know where are the ions at this point. So it might be helpful just to apply a certain voltage for a certain time, and then you know, okay, now I assume my ions are on this and this side, for example. And then what's interesting is we have implemented the so-called user-defined techniques. We have plenty of predefined techniques like CELIV and so on, but if you have a known idea for an experiment you would like to try, you can just, with some simple formulas, what you see here, so some algebraic expression, you can kind of design your own signal and then just run it and see if it's worth. So without any complicated coding or cabling or whatever, it's very, very easy to do. PAIOS comes with plenty of modules, so we just started with this blue box, and then we added more and more additional modules with it. So one of the first ones was a low temperature module. So this is the low temperature module that comes with liquid nitrogen. You see here, this is a dewar, so here you need to fill in liquid nitrogen, and then your cell is in here. And with this you can cool down your device, and PAIOS does all the controlling. So in the end, you don't need to be there. You can just plug your device, press start. PAIOS does the controlling and then measures all the techniques at all the temperatures. And you get a very nice set of systematic data as you see here. So you see here it's indicated red is a hot temperature, blue is cold, and it's perfectly very nice systematic. And then it's very, very easy to study physics. We have now a new cryostat that we have here. We don't have it now running for the demonstration, but I'll quickly show you. You put your device on here, and then there's illumination from the bottom, so there's a certain distance between, and we have a light mixing rod in between because it's important. We don't want to measure the heat of the LED. We just want to measure the device, and this setup here is with Peltier element cooled, so you don't need any liquid nitrogen. That's good when you want to measure a very long time, because, for example, when you want to measure impedance spectroscopy at 10 millihertz of a perovskite solar cell, you may want to measure it over the weekend, and you would need to fill this nitrogen dewar every 5 hours or something like that. And this here, the Peltier cryostat, you don't need to refill because you only need to plug it into plug it onto the grid, and it cools by electricity. Of course, the drawback is here you reach minus 40 degrees, and with the liquid nitrogen you can go way below minus 100 degrees. Then we have implemented a spectrometer. It's mainly useful for OLED, so you can measure the spectrum, and then you can show it here in this nice CIE graph. You can show the color and then also compare the different colors. And then we have added an automated measurement table. This is what you see here. So there's different instruments. You see there's a fiber for the spectrometer, there's a photodetector, and there's a LED. And the system automatically rotates to choose which one is the most relevant. Then we also do stressing. So this is then will be possible with the new stress test setup in even in parallel. So the current system here, this is like serial stressing. So you just stress one device. But what's interesting also here, you get very systematic data. So you can plug your device once, and then you say, I want, for example, stress it with light for half an hour. And then I want to perform all different experiments, and you get very systematic data. As you see here, this is a study that Simon Züffler did on an organic solar cell that they degraded, and you see here nicely how it's systematically degrading. So this is then initial, this is the start, and this is then how the current develops until the current is completely flat when the cell is fully degraded. And he made a very nice publication here describing with simulation exactly what's happening. We also offer like customized sample holders. So in case you don't want to put and contact the stuff here manually, it's much more convenient, of course, to have a customized sample holder where you just need to put in your sample and then contact it directly. It makes just everything a bit easier. Okay, so this is now this was the PAIOS system itself. What we have now connected it, and kind of it's like a marriage with the simulation software, because once you have measured all your measurements, all your devices, you may want to learn something from it, and the best way to learn something from it is by comparing it to numerical simulation. So that's what we call PAIOS ZFOS integration. So you can define, as in ZFOS, you can define your layer structure, but what you don't need to define is all experiments. Because the experimental techniques, so for example in CELIV, what is exactly the ramp rate and so on, what is the light intensity, PAIOS knows already because it has performed the measurement and has stored all the settings. So when you want to simulate, you only need to define what you want to simulate, so your layer structure and your parameters, but not more. And then you can directly, in the software of PAIOS, you can directly compare simulation and measurement. As an example here, so you see this is open circuit voltage versus light intensity. The solid line is the measurement, and this here is the simulation. This is an example where it does not agree, so you would need to tweak some parameters to make these two lines agree. This tweaking sometimes may be a bit tedious, so that's why we have implemented a fitting routine, where you define your parameters and some boundaries and so on, and then you can let the software optimize the whole thing on its own. So it starts doing simulations and then adapts the parameters to bring measurement and simulation into agreement. So simplified speaking, this would look like this. First you have, so this is an IV curve in light and in the dark. You have some initial simulation here where it doesn't match. You define some parameters you want to tweak, and then the software does it, and half an hour later or even less, you see you have a nice match, and simulation and measurement agree with each other. So that's our way on how we understand parameter extraction. So this is how it looks in the software. So this is a capacitance voltage curve of an organic solar cell where we do some global fitting, and you see this is where it starts, and then you see here, for example, this is how the fit, what was reached. So you get an easy fit. Before in my talk, I showed this correlation matrix. So this gives you an information about how unique is your fit that you received. And this is automatically calculated in PAIOS, and you just can have a look at it and see, okay, this and these parameters are correlated, so I cannot trust these parameters as much as the others. So now I want to show a quick OLED example, because now I've mainly been talking about solar cells. So an OLED example that we just recently did is this here. You see now the purple line is the measurement, and the blue line is the simulation. So on the top left, there is just an IV curve. You see here the dark IV fits, the reverse IV here fits as well. You have here some deviation, but here the whole dynamics, consider this is a log-log scale, so this is a very nice fit. Then here we have Transient Electroluminescence. So you turn on OLEDs to a certain voltage, so let's say to 5 volt, and then you measure how the electroluminescence increases. And also here we get a very nice fit. So you see the blue line here, you almost don't see it because it matches perfectly. And the same for the decay. So this is when you turn off the light. So you see there's two regimes. Here is a exponential regime 1, and then here there's another exponential regime, and we can catch that by the simulation quite well. On the other hand, on the bottom, you see some experiments that do not match. So you see here, for example, the capacitance voltage. So here the simulation is way off. And also here in the injection CELIV, so we extract much more charge that is actually extracted in the experiment. So this is work in progress. So what, for example, could be done is to add traps. So when we add, in the previous simulation was without traps. When we add traps, what happens is then that this peak here decreases. So less charge is extracted in this case. So the software makes it as easy as possible to extract all different kinds of parameters. So here I have a small list on what we can learn from all these techniques. So we can study recombination by different techniques, or for example by so-called Otrace CELIV. So Otrace it's a bit like you create charge carriers and you wait a certain time and then you extract the charges and you repeat this measurement with different delay times, and like this you can extract the bimolecular recombination rate, for example. We can do transient photovoltage or IMPS. With this we can extract information about the recombination. We can measure the mobility either with Photo-CELIV, what I already mentioned. We can do it with transient photocurrent. Also there the mobility has a high influence on the shape, on how the current goes up. Or we can do, of course, the simple Mott-Gurney fits of an IV curve. This, however, only works in monopolar devices. We can measure the charge carrier density at VOC using charge extraction. We can measure the doping density using the dark CELIV. This is what I showed in the talk before. So you just measure how much charge is extracted in the dark. With this you can estimate the doping density, or you can do it with the simple Motrutki analysis by analyzing capacitance-voltage curves. You can investigate charge injection by CF, for example, and also CELIV can be quite sensitive to charge injection. You can investigate traps by looking at the low frequency behavior of impedance spectroscopy. So this is what you see here. Very often when you have traps or stuff, you have an increase in the capacitance here at low frequencies. In transient photocurrents, traps can also lead to distinct features. So sometimes you also see an overshoot, so the current going up and then going down again, for example. So this is also interesting to investigate traps. And of course you can do the dark IV or the VOC versus light intensity curve to measure the ideality and to find out if your device is limited by traps or not. Then we have implemented techniques to easily extract the series resistance. Usually we do this from CF or from dark CELIV. And from the same techniques we can also extract the electrical permittivity or the capacitance. So this is a bit an overview on what we can learn from all the different techniques. So now I would like to switch to this computer. Well, let me see. I need to push here somewhere. All right, so I can make a small demo. So I contact here an OLED. So you don't see it well, but now below is the photo detector, and I now just close the lid because the measurement quality is better if we don't have the environment light. So, and now let's just open a new file in PAIOS. So this is here, you see the software interface. And first what we need to do is we need to define a so-called measurement procedure. So I just start with a very easy technique, like let's say we just measure an IV curve of a solar cell. So here we can define the parameters we want to measure it. Whose OLED is it? Because Sandra's OLED. Okay, I don't know how much volt I can apply, but let's just go to 5 volt. If I destroy it, it's your fault, Simon. No, we'll see. So here you can define how fast the ramp is. So let's say 600 milliseconds, and I just quickly perform a test measurement. It now measures a whole ramp, and it goes quite quickly. So you see, this is the, oh, hopla, this should not be in lock. So this is the current, and this here is the electroluminescence signal for the OLED, just a quick test. So let's say this is now our first technique. Let's add another one, for example, Transient Electroluminescence. So this is basically a voltage pulse where we also measure the light intensity. So let's say, I think 100 microseconds are probably enough. And we go to, let's say, 5 volt also. Let's say start. All right, so let's first look at the current. You see there's a large peak. There's a displacement current. Maybe I take this here. Oh, now it doesn't work. Okay, now I can also show it with the mouse. So there's a large displacement current here. This is because of RC effects, and then there's also a small steady state current. What we can do here is we look at the electroluminescence signal, and you see now there's some noise, because apparently the signal is very weak, but we see there's some noise at the beginning, and then the EL signal rises. What we can now do to improve the signal quality, for example, is we can just go here and say we want to use a certain gain. So the photodiode has different gains. When we measure it here, now it looks much better. So before I mentioned that you can do lots of varying parameters, what we call sweeping. I can do that now, for example, saying we vary the voltage, so we go from 5 to 6 volt, and let's say we make 4 steps. So you can see here a preview what we are going to do. We press now start. It does now all these 3 measurements. And now you can play here with the data by just like using this slider. You can also show all of these, and you see the higher the voltage, the faster the onset. So this is what we expect. Let's add maybe one more technique. Let's add impedance spectroscopy. I only go to 100 Hertz, otherwise it takes a bit too long. We do just impedance spectroscopy at 0 volt. So let's do a test measurement. So now here you see it starts, so this is the frequency, so it starts at the higher frequencies and it goes down to lower and lower frequencies. With PAIOS we can go down to 10 millihertz, maybe even 1 millihertz, but we have never tried because you can imagine already 10 millihertz, it takes a while, so you need to measure it over the weekend. It takes so much time, but we are also capable to go down to very low frequencies. So now we can, for example, look at the amplitude here, or the phase. In this case, it's apparently a device where not much happens. So you see the capacitance is quite flat here, so there's no sign of traps. When we now would apply an offset voltage, we would see there probably a different level. So now you can here define as many techniques as you want. And the way you work with PAIOS is that you go to acquire and manage data, and here we can define different cells. So for example, we can say this is our test OLED 1, and I can now press start, and now everything is measured after each other automatically. So you can go and have a coffee, and when you come back the measurement is finished. So let's quickly finish this one here. Okay, so here are now our data, and let's now assume we want to have to compare it to another device. I just connect here. So this is a different OLED. Let's just see what happens when I connect this one. Oh, hopla. since we have now already defined this technique, we can just say, we just add another device and say this is our test, test OLED 2. You can say start measurement. And again, it's being measured automatically. And while it's measured, we can already have a look at it. So for example, we can now say, we just compare both of these devices, and we can now still play with the data and here analyze the EL. You see, apparently it's just a little less efficient, or I did not place it exactly in the same position as before. But you see that the handling, it's easy. So here the current is very, very similar. Apparently, when we look at the EL versus voltage, is also similar. But it's now very easy to compare these two OLEDs with each other. Of course, you can compare as many as you want. So let's quickly show you one example how this basic post-processing works. So this is what I've shown before, is basic because it's without numerical simulation. So you go here and say basic post-processing. You see this is a whole bunch of techniques that are available here. Now I say I want to extract the mobility from the EL turn-on. Just briefly how this works. So we say when we start the voltage, the light doesn't come out immediately. There's a certain delay time when the light starts. And what we now do is we say, okay, let's take this delay time, and we have a certain device thickness, and from that we can calculate the mobility, because it takes a certain time until two charge carriers have reached each other in the middle of the device or somewhere and start recombining. Of course, it's a very simplified image here because we just take an average. So what we can do here now is now you see there's a lot of noise, so what we can do is we just activate the filter, so then it works a bit better, and we may increase the onset level. Okay, so now you see here the red point is the level where it has recognized the onset, and here at the bottom you see the mobility. So it's here apparently around 2 times 10 to the minus 6 centimeters squared per volt second. So this is a rough estimate of the both mobilities together in this OLED. And you will see here in the x-axis, this is the electric field, because we have done it for different voltages. So here it's a surprisingly linear behavior. Interesting. All right, let's now quickly make another example of a solar cell without saving this one here. Oh, by the way, if you have questions, just feel free to ask in the middle. All right, so we measure a solar cell now. Just add an IV curve and quickly need to exchange the device. So it looks very similar as the OLED, but now it's a solar cell. We measured the voltage from minus 0.5 to 1 volt, and we vary the light intensity. So let's quickly see. You see now it's changing to the LED. Before it used the photo detector, now it's swapped automatically to the LED, and there we go, it starts measuring. So I quickly close here the lid so we have a bit better measurement quality. Oh, and there we go, this is our IV curve. And we can, for example, also do transient photocurrent. Say we do it here with three steps. And now you see how the current is going up. So here at 0 the light is turned on, and at 200 the light is turned off. And you see here how the light goes up and how it decays again for different light intensities. And there's plenty of other techniques that I could show you now. Some of them take a bit longer, but let's quickly do one CELIV experiment, because that's quite interesting. So now you see here an example of that. There is what we do is we apply here a linear voltage ramp to the negative, and we before illuminate the solar cell with varied light intensities. So here I can hear varied light intensity, and or maybe 1% is enough, and I only measure 4. So So it goes a bit longer. So you see a preview of what will be measured. And what we do here is we set the offset voltage, so the voltage here before, it should set it automatically to VOC. Because in CELIV, we want to have the device at VOC such that the current is 0 initially, and then we go with the ramp. So there should not be no injection or extraction current. And PAIOS does this automatically. There's also a possibility to do Otrace. This is the technique that adapts the voltage TK to a TPV decay such that you don't lose charges in the meantime when you have a delay time between the light and the measurement. In this case here, you see this is the light intensity, the red one. We don't have any delay time, so the delay time is 0. So let's say start. You see, this is now a classical dark CELIV, so that you don't see any overshoot. And now an overshoot starts. You see, the more light, the more charge we have that can be extracted. So this is what you see here. Now I can still play with the data. So this is dark IV, no charge is extracted. And this is with the full light intensity and with the steps in between. So you see, it's quite easy to do different experiments with it. Now I would like to show you quickly, very briefly, how the simulation integration with the simulation software works. For that, we have here so-called device definition. Let me see if it runs. Yes. Here we can, for example, load something from a template. We can say we take a regular organic solar cell. Quickly change here to ohmic. So we can say open setphos. And now you see this is the setphos GUI. The one of you that know it may recognize part of it. It's not exactly like setphos because there's a lot of stuff that is disabled. So what you can do here, you define your layer. So for example, here you see you have an ITO layer, P dot, then the polymer in the middle, and some aluminium. And here you see a graphical display, and you see the energy diagram. And for example, here you can now go and define exactly what N and K values you want to use, or you can define the HOMO level, LUMO level, and 0, the different mobilities, and so on. So once you have done this, you can go back. And now everything is ready for the first simulation, so we can go here and say which is simulate an IV curve. Here, are some numerical settings, what you actually want to simulate, and then we say start. Now, let's see what happens. Okay, so this is a simulation server. This is a simulation manager, and there's different servers that are available for simulation, so you can also distribute. So, for example, if Simon now had his computer in the same network, and he would have been running this simulation client, the simulation server actually, it would appear here. So I can easily distribute my simulations on many different PCs. That's very good when we do fitting to speed up the whole procedure. Now you see it's already finished. We can go down here to plot settings, and we see now here the light, the solid light, thin lines. This is the simulation, and this here is the measurement. So you see now in this case it doesn't really agree. So what we can do is we can say probably the charge conversion needs to be a bit better. So we can go back and say optical charge generation, let's put this to 1. And what else should we adapt? Maybe the work functions could be adapted a little bit. So we decrease this here a bit and increase this here a bit. So we can go back and say simulate. The simulation is usually quite fast. So you see now already the current at least matches, and the VOC got a bit better. So here we can start playing with all these. So let's say we have now a device here that we quickly measured, solar cell. For example, what one could do is one first measures a CELIV, extracts some mobilities there, and then uses the simulation to resimulate the solar cell. What I actually did not yet use is probably the thickness. Well, yeah, it doesn't matter, it's just an example. All right, so here we can also, before I just simulated an IV curve. I can also simulate, for example, the transient photocurrent. So let's quickly put some good settings. I can say how many points should be calculated and what residuum it should take. And you see here, this is now again the simulation. You don't see it very nicely. Let's put it in logarithm. You see again the simulation and the measurement. And of course, because now it's just some initial parameters that I have not tweaked, it doesn't really fit. What you see, it's very, very simple to directly compare simulation and measurement. So it's easy to understand and easy to use. And if you have different solar cells, you can manage everything here directly in this software. Okay, so that's basically the presentation. So I'm happy to take any questions if you have.